Okay, so we are recording. So welcome everyone to this analysis junior seminar. Today the speaker is Adriano Prade from École Polytechnique in Paris, and he's going to speak about Young's law and regularity of minimizers for a non-local isoperimetric model of charge capillarity droplets. Please, Adriano.
Okay, thank you very much, Nicola and Marco, for the invitation. Today I'm going to talk about a joint work with my supervisors, Michael Goldman from École Polytechnique and Matteo Novaga from the University of Pisa. And the talk will be divided in three parts. First of all, I will introduce a model for the charged droplets, and I will review the state of art from literature after explaining the physical situation. Secondly, I will focus on another model, this time for describing liquid droplets leaning on a surface. So I'm going to talk about some capillarity theory. And finally, in the last part, I will combine the two things, the two models, and I will consider charged droplets that are also leaning on a surface. Okay, so let me start from the physical situation we want to consider. We want to consider a charged liquid droplet in absence of gravity. So you can think about a situation similar to the one that you can see in the picture. We represent the droplet as a set E in R3, and we fix its volume to be 1. And then we can represent the electric charge as a measure. The measure is confined within the set E, so its supports is contained in the set. And we ask for it to give a weight Q to the whole set to say that this is just the charge Q. And there is no gravity, so there are two forces that are acting on the system. On the left side here, you can see, first of all, the cohesion forces between the molecules. We have two different possibilities. So in this system, there are two phases, a liquid phase within the droplet and a gas phase, the atmosphere around. So if we pick a particle in the interior, then it's being pulled from every direction by all of the other particles surrounding it. And for this reason, the equal force will be roughly 0. But on the other hand, if we pick a particle which is at the interface between the liquid phase and the gas phase, then it's going to be pulled only from one side. For this reason, the overall force will be non-zero, and the surface area of the droplet will try to shrink to the minimal area possible. These are the cohesion forces. On the other hand, we all know that whenever we have some charged particles, here I represented the measure in red. If we take every couple of charged particles, x and y, we are going to have a repulsive force between the two of them, for which its module, it can be expressed in this way. It's proportional to the inverse of the distance multiplied by, 1 over 4 pi times 1 over the permittivity of the vacuum. So this is more or less what happens. So as I said, the first force can be represented by the classical perimeter. Indeed, the perimeter multiplied by a coefficient called the surface tension coefficient, a positive coefficient, can be seen as a measure of the surface tension of the droplet. And it's a local force because it only depends on a neighborhood, and it's also attractive. It has an attractive force on the droplet. Secondly, in the case of the Coulomb interaction, before I showed you only the interaction between two particles, if we consider every couple of charged particles, we make them interact via double integral. So I take the double integral and I consider again the Coulomb kernel multiplied by the same constants. And since the charge is able to move within the droplet, it's going to try to get to the configuration of minimal energy. So for this reason, we take the infimum over all of the measures that are supported in E and that give weight Q to the set. Okay, so how can we represent what's happening? Well, the idea, we want to study the possible equilibrium configurations of the droplet. And for this reason, we want to sum up the two terms and study the minimizers of the geometric energy functional that you can see here. So a perimeter term plus a Coulomb term This one I'm gonna call it Riesz energy, and I will define it in a second. And the idea is that the droplet is subject to these two forces, so it's gonna try to change shapes, to change shape, and this is why we want to look at the minimizers. And we also fix a volume constraint. This model is, I would say, quite classical in the literature because it was proposed first by Lord Rayleigh in actually in 1882, so quite some time ago. But later on, it was studied more or less in the last 10 to 15 years. Okay, before talking about some mathematics, I would like to focus on what we expect from this model. There is also some scientific literature, which is not only mathematical. We have something from physics and chemistry. In particular, it was seen from the experiments that if we take a slightly similar situation, so a charge droplet E, which is exposed to an electric field, so there is still some electric interaction, we can see that there is a critical charge, strictly positive charge, such that if our charge Q is below this critical charge, then the surface tension dominates, namely the perimeter term dominates, and the droplet remains stable. Remains stable in the sense that it maintains a spherical shape, and this is the expected minimizer of our functional. On the other hand, if the charge increases, or we increase the intensity of the electric field, in this case, the repulsive forces between the molecules are dominating, and the droplet, the surface of the droplet starts developing singularities. In particular, what happens is that as long as the charge increases, first of all, we have, you can think about a sphere, then it starts distorting into a cone, and at some point there is a breaking point in which we lose connectedness of the set, and the big droplet realizes a lot of really small and with a very high charge, basically a cloud of droplets which are highly charged. And this is an interesting phenomenon because it has many applications. Among those I listed, I would like to cite the first one in mass spectrometry. The idea is that you have some liquid which has some charge in it, and you want to measure. The charge, so you expose it under the action of an electric field, and in this way, with the same mechanism that I described, it's going to realize all of the particles in the air, and you will be able to measure it. Another thing I didn't say, let me just come back to the previous slide. Well, the Riesz energy term that I described here, it's non-local because every particle is interacting of every other charged particle regardless of the distance, and it's also repulsive. Why? Because since we have the Coulomb kernel at the denominator, the closer the two particles, the higher will be the interaction. Okay, so as I said, as I said before, there is a competition between the two terms. One makes the droplet stay together, the perimeter, and the second one makes the droplet crumble in some sense. Okay, but let me pass to some mathematics. So I would like first to introduce the general definition for this object. Let me consider any dimension greater or equal than 2 and fix a parameter alpha between 0, comprised between 0 and n. Then we call the alpha Riesz energy of a set E over n. It's the same expression as before. We take a probability measure this time, so weight 1 to the set, and we make it interact with itself via double integral. And we multiply it by 1 over the distance of every couple of particles to the power n minus alpha. Again, we think that the charge is free to move and free to acquire the configuration of minimal energy. And so we take the infimum over all of the measures, all of the probability measures who are supported in the set. This is called the alpha Riesz energy of the set E. And we can already notice that if we replace n equal to 3 and alpha equal to 2, we have exactly the same expression as before up to constants. So this is why I had put a number 2 here instead of alpha. So this object has many properties. I would like to go quick in this part. I just want to mention that if the set E, pretty natural to ask when this infimum is also a minimum. Well, this happens for sure if the set E is compact. It's possible to prove that there exists a unique so-called equilibrium measure, which I will denote by mu of V, such that we have exactly like the infimum is a minimum, indeed. And we can also say other things, in particular, if the parameter alpha is between 0 and 2, then the support is on the whole of the, in the whole of the set. If the parameter alpha is between 2 and n, and so this is also the natural case, the Coulomb case, then the support is on the boundary of the set. I put a diagram to make the situation a bit more clear. Again, we consider the Coulomb case, so dimension equal to 3, parameter alpha equal to 2. You can think about a big conducting body, this set E, like a metal body. Well, as it happens in reality, also with the Riesz energy, the charge concentrates on the boundary, as I said here. And it's also interesting to see that whenever the curvature of the set is higher, so for example here, this kind of spikes, or even when the set is singular, the boundary of the set is singular, the charge will try to accumulate there. Why? Because in this way, the energy, the overall energy will be minimized. This is basically what we can observe and also prove mathematically. I want to introduce the same object, so the Coulomb case, but not in dimension 3, also in dimension 2. In this case, I cannot pick the parameter alpha equal to 2 using this kernel, but I'm going to use an alternative definition, which is the so-called logarithmic energy. We take again a double integral for a probability measure. Here we are in dimension 2. And instead of using the Riesz kernel, we use the so-called logarithmic kernel. And as before, we can see that in this case, if our set is compact, there exists a unique equilibrium measure, such that we have this equality and the infimum is a minimum. And as before, it is supported on the boundary. So here I put the exact same diagram to show you that we have basically the exact same phenomena. And this can be considered also for other deep reasons, the equivalent of the Coulomb case in dimension 2. And this will be important because we will use it later in the talk. Okay, so now as before, we can define the functional we want to work on. So you can think about a set E in Rn, which will be our droplet in absence on gravity. You fix a positive charge Q, and we define the functional by summing up the classical perimeter of the set plus the charge to the power 2 multiplied by the Riesz energy. So you can see that up to constant, this is a generalization in dimension n, and with any parameter alpha of the model that I introduced before. We want to study the problem that you can see here. So we want to find the configurations of equilibrium to minimize the energy of these sets whenever we fix the volume. And here omega n stands for the volume of the ball of radius 1 in Rn. And as I said before, there is a competition also in this general version. So the perimeter term is local and attractive, and we can see it from the real classical isoperimetric problem in Rn. We know that if we minimize the perimeter among all of the sets with volume, the volume of the unit ball, we will get, of course, the perimeter of the ball. The unique minimizer is a ball. And on the other hand, as before, the Riesz energy is always non-local and repulsive. And quite an interesting thing is that if we take at least the range of exponents between 0 and 2, and you maximize the Riesz energy with the same volume constraint, well, in this case, you find exactly the Riesz energy of the ball. Why? Because the ball is the most like symmetric set possible in some sense. There are like no spikes and no singularity. So the charge will assume a symmetrical configuration and it will maximize the Riesz energy. So you can see here that there is really a competition. And so it's a problem that is non-trivial to study. What do we expect? We expect something that is similar to what happens in the experiments. Because I mean, this is more or less the purpose of the model. Like we introduce mathematical objects to study what happens in reality. And so we also want to prove basically the same things that happens in the experiments. So as I said before, we expect that if the Q is very small, then the perimeter term here dominates. And maybe we can hope for existence of minimizers and their stability. But if the charge is too big, then we would like to find the non-existence of minimizers or some kind of singular behavior. Let me introduce, oh wait, sorry, I had a mistake. Okay. Let me now introduce some results from the literature regarding this functional. So the first result is quite surprising. Any dimension greater or equal than 2 and any charge, any positive charge, we consider the range of parameters alpha between 1 and n. Well, it was proved that if we look at the infimum of this energy whenever the volume of the set is fixed, then we find exactly the perimeter of the ball. And this is a catastrophic thing. Why is it very bad? It's very bad, I'm sorry for the banners, because if you look at the Riesz energy of the ball, as it's written here, this is positive. So this means that if you sum up the two terms, what you would expect for at least small charges does not happen. In the sense that it's impossible to minimize this functional whenever you have a volume constraint. And why is this bad? Because this happens for every charge Q, so even very small charge. And this happens also in the physical case that it was n equal to 3 and alpha equal to 2. So in this case, it's part also of this range. Not only the functional has no global minimizer, it was proved in the same work that it has not even a local minimizer, neither in the L1 nor in the Hausdorff topologies. In particular, as I said, as I've just said, in the physical case n equal to 3 and alpha equal to 2, we have ill-posedness for every charge. And this is against what we observed in the experiments. And there's also some numerics regarding this model. And also in that case, it was possible to prove stability for small charges. And yeah, so it's also against the numerical results. So what does it mean? Well, it means that the model is wrong, in the sense that, as I said, we want to describe something that happens in reality, but on a mathematical level, this does not happen, and so we have to modify the functional. Before doing that, very briefly, I don't want to spend too many words on the proof, but the idea of this proof is that you want to build a minimizing sequence for this energy, such that the perimeter of the sets of the sequence is converging to the perimeter of the ball, and the Riesz energy is converging to 0. So in this way, it's actually possible to see that the infimum of all the possible energies is exactly the perimeter of the ball. And it's interesting to see that this is possible to build regardless of the charge. And we have a phenomenon very similar to what happens in reality. So a sort of like a cloud of really small balls with a lot of charge concentrated there is created, and this happens for every charge. So what I want to tell you from all of this is that the enemy here is the very high concentration of charge. So the idea is to prevent this mechanism. Okay, so we want to modify this functional. How do we do it? We can do it in two ways. Either modify the class of sets, the class of competitors, or we modify the functional itself, or a combination of both. So a possibility is to change the class of competitors, like Michael, Matteo, and Berardo, who proved this first result. Consider first C11 sets with the delta ball condition, and they were able to prove well-posedness in that case. And secondly, in another work, they focused on the class of convex bodies, and this is what I will focus on also in this presentation. I will come back to this later. Another possibility, as I said before, our enemy is the concentration of charge, and I said that this happens when the curvature of the set is really high. Well, if we add a Wilmore energy term, so the integral over the boundary of the curvature of the set to the power 2, and we add it to our functional, this can be finite if and only if the curvature is in L2. So in this way, it can explode only in a controlled way, and also the charge cannot concentrate too much. In a similar way, we can also modify the Riesz energy itself. We can add an entropy term. Basically, we ask the measure mu to be in L2, and so we add its L2 norm multiplied by epsilon. And in this way, there is also an optimal charge, and studying the equivalent functional, it's possible to prove well-posedness for this model. Now you can also wonder, before going on, what happens in the remaining cases, namely here we have only the parameters between 1 and n. What happens in the other cases? Well, quite ironically, another result proved by Michael, Matteo, and Berardo, if you consider the remaining cases, it's possible to prove well-posedness for the model, and also that there exists a small charge such that if the charge is small enough below this threshold, then the balls are the only minimizers of the problem in a pretty natural class of sets. And I mean, the mathematics is very clear here if you read the article, but I still find it a bit ironic in the sense that in the non-physical case, because this is non-physical, you can prove exactly what you would like to have in the physical one. In any case, this is a very beautiful result, in my opinion, and I would like to advertise the article. If you ever happen to see it, I found it very nice. Okay, but let's focus on what I said before. So the class, let's impose convexity of the competitors. So same function as before, we consider sets with the same volume, and we ask the set, the competitor, to be a convex body. What is a convex body? To me, a convex body is a convex set in Rn, which is compact and which has non-empty interior. Why is this like a reasonable assumption for our relational problem? Because first of all, convex bodies, they have good compactness properties. It's enough to give a bound to the diameters of the members of a minimizing sequence. Secondly, from the experiments, we know that if the charge is small, then the stable set, the equilibrium configurations for the droplet are balls, which are strictly convex. And so it's fair to assume the same also on a mathematical level. And what was proved in the work that I briefly cited before is that for every charge, it's possible to find a minimizer for this problem, asking convexity. And in the Coulomb case in dimension 2, so n equal to alpha equal to 2, logarithmic kernel, then the minimizers are of class C11. And there is a charge such that if the charge, like a critical charge, such that if you are below this charge, then the only minimizers are ball. And this is very good. The result is quite remarkable because, okay, I told you that convex sets are good for existence, but proving regularity is always tricky because the idea is to either use a competitor argument or to make some kind of variation by changing the boundary of the set. But if the set is convex, it's a bit hard to make variations and remaining in the class of. For example, if you have a flat line, which is something convex, like a half space, for example, how can you modify it locally in order to get a variation? But we will come back to it later. What I want to focus now is the so-called capillarity theory, which aims at studying a similar situation to the one that I described, involving liquid droplets, but this time, instead of being in absence of gravity and with a charge, they are laying on a surface. So what's the situation? So we can consider to work in the upper half space of Rn, x3 greater or equal than 0. And as before, we describe our liquid droplet with a set E contained in this half space, which is also leaning on the boundary. So as you can see here, and again, we ask the volume to be 1, and we have no charge. So the main difference from before is a contact set and the lack of charge. This model is quite similar to the other, but the main difference is that here we don't have only 2 phases, but we have a third one. Indeed, we have a liquid phase, the droplet, a gas phase, the air surrounding the droplet, but also a solid phase. So for this reason, we have three different types of interface between the solid gas, liquid gas, and solid liquid phase. And not only we have cohesion forces between the molecules of the droplets, but also adhesion forces with the containers. And it's interesting to see how they interact with each other. And we are going to have three different coefficients of surface tension. And well, what we can see, the main feature of this model is the so-called Young's law. If you look at a contact point between the droplet and the surface of the container, and the droplet is in equilibrium, so it means that it's still. Well, if you make your diagram of forces along the horizontal line here, you see that the first one here must be equal to the sum of the second one times the third, the cosine of the angle that I denote by gamma. So if you express the cosine of the angle with respect starting from this equality, you find exactly the so-called Young's law, which basically depends on the physical and chemical properties of the material involved and completely characterizes the contact angle between the droplet and the surface. We can also describe this problem in a mathematical way. Some people in the audience already know it. Let me introduce the so-called, I will call it capillarity perimeter for short. The idea is to think about your droplet in the half space in Rn. You want to take the area of the droplet inside the container minus a parameter beta between -1 and 1 times the area of the wet part between the droplet and the container. Indeed, we call the second term wetting energy. And the idea of the parameter beta is that it weights the action of the cohesion forces within the droplet against the action of the adhesion forces between the droplet and the container. But we will see it in a second. So to look for equilibrium configurations, we want to look at minimizers of the variational problem here. So again, we prescribe a volume 1. And it's quite classical to see that this kind of perimeter term is lower semi-continuous when the parameter beta is in the right range of between -1 and 1. You can find everything, for example, in Magic's book. And before being a bit more specific, I would like to highlight that if beta is equal to exactly -1, then we are minimizing the perimeter inside the half space, the constraint isoperimetric problem, and so minimizers are ball. If instead the parameter beta is equal to 0, this is the relative isoperimetric problem, and instead of having balls, we have pieces of balls arriving at 90 degrees. So maybe you want to see where I'm going to go, but what is interesting is that if you study the equilibrium conditions for stationary sets of this variational problem, you can see that, well, in the interior, you have the classical condition that you have also for the classical isoperimetric problem with the perimeter, namely that the mean curvature of the set must be equal to a constant. So at least in dimension 2, it means that in the interior, we're going to have pieces of balls. Secondly, we also have a boundary condition given by the capillarity contribution of the functional that it can be expressed either with the two outer normals, but with the most important feature of the model, namely the Young's law. So what we have is that the cosine of the angle between the normal to the droplet and the normal to the container is exactly equal to the parameter beta. In addition, you can also completely characterize the minimizers. Well, it turns out that whenever you fix a volume, the minimizers are only truncated balls that are laying on the boundary of the half space, and they are truncated in a way that they satisfy Young's law. Let me be a bit more clear with an example. Well, here above you can see the two examples from before. If you take a parameter beta between -1 and 0, this means that the cohesion forces of the droplet are winning against the adhesion forces, and an obtuse angle will be created between the droplet and the surface. And this is the so-called lotus effect in applications. It's quite fun. If you look up for lotus leaves with a droplet on Google, you can really see this phenomenon happening in reality. And on the other hand, you have, whenever the parameter beta is between 0 and 1, the so-called petal effect. So in this case, the adhesion forces between the droplets and the container are winning, and you can see an acute angle, an acute contact angle. And both of these two phenomena have applications in reality. And we can see how we can fully describe what happens on a mathematical level in the framework of capillarity. Okay, so now I can combine the two models as I anticipated before. Now we want to consider, again, a droplet which is landing on a surface, but also with a charge. So as before, exactly the same situation, we consider a set E in the half space, which is adherent to its boundary and with a fixed volume. And we consider a probability measure, which represents the electric charge. It gives weight 1 to the set, and the support is in the set, exactly as before. And we will multiply it by Q to get the value of the charge Q. Again, we have a competition between two forces. The surface tensions given by the interactions between the molecules, and this is always a local force. And then the charge repulsion, which is, again, non-local and repulsive. A main application of this is the so-called technique of electrowetting that you can see represented here. You can consider a charge droplet, which is placed over an insulating coating here, and which is also placed over a metal electrode in gray here below. And if you apply a difference of voltage between the droplet and the electrode below, the whole system acts as a capacitor, and it's possible to observe on an experimental level a flattening action for the droplet. Namely, the droplet gets more flat. And this is quite important in applications. I am not an expert, of course, but if you can ask me, like, if someone is interested, I can also give you references later. And how do we model the situation on a mathematical level? Well, it's pretty intuitive that from everything that I've told you so far, it's gonna be enough to consider, again, there is energy to represent the charge, plus, instead of the perimeter, the shape functional that I called capillarity perimeter. And we wanna study this functional and answer classical questions in calculus of variations, but we directly impose convexity of competitors. Why? Because also in this case, we expect the same ill-posedness phenomenon, which was proved by Michael, Matteo, and Berardo, but with the presence of the perimeter instead of the capillarity perimeter. Okay, so for any dimension n greater or equal than 2, and for every parameter alpha between 0 and n, or in the logarithmic case, whenever beta is between -1 and 1, and whenever we have a positive charge Q, we want to look at this variational problem, so the minimum of the energy, asking convexity of competitors, and asking also a fixed volume. Okay. So asking convexity is quite good, because as before, we can always prove that we can always get existence regardless of the charge, namely for every charge of the parameter beta and of the choice of the parameter alpha. And another interesting thing, it's the fact that whenever the charge vanishes, we have also the convergence of the minimizers of this model with the Riesz energy to the minimizers of the capillarity perimeter. And I'm going to show you real quick the proof. Well, the existence comes from giving a uniform bound to the diameters of the sets of a minimizing sequence, and the fact that we can easily control the capillarity perimeter with the perimeter, and then we can apply compactness of convex sets. And the proof of the convergence statement is quite interesting, and I decided to report it because it's an application of the quantitative isoperimetric inequality, which was proved for in the capillarity framework. The article came out a couple of years ago, and it's from Giulio Pascale and Marco Postetta. We can see the application of the inequality here in the first one. This is the symmetric difference between a minimizer of our model and a truncated ball that minimizes capillarity. And if we take it to the power 2, the measure of the symmetric difference, it can be bounded from above by the difference of the two perimeters, or the capillarity perimeters. Then we use the fact that E is a minimizer for our functional, and the truncated ball B beta is a competitor. And we rearrange the term. In the end, it's possible to bound uniformly the Riesz energies of the both of them. And we can see that the left-hand side is bounded by the right-hand side. So whenever we send the charge to go to 0, we can immediately see L1 convergence as soon as the charge vanishes. Okay, now we focus on the planar logarithmic case. So instead of considering the alpha Riesz energy, we take its logarithmic counterpart. And we want to answer to, okay, can we prove regularity away from the contact points? First of all, because, okay, we expect for the convergence statement of before that the minimizers will have some contact set as the minimizers of the capillarity perimeter. And so it's very natural to ask, do we have also the validity of Young's law? Well, a first step, I reported it, but I want to be very brief about it. We get rid of the volume constraint that you can see here above. And this is quite a classical procedure in isoperimetric problems in calculus of variations. It's sufficient to add a penalization of the volume, and it's possible to prove that minimizers of the first problem are also minimizers of the second one, and vice versa. And if we adapt the argument by Michael, Matteo, and Berardo in their article, where they consider the same functional but with the perimeter, it's possible to see that the minimizers, the interface between the liquid part and the gas part, this is C1 lock regular away from the contact points, which means, I didn't say it before, that it can be locally represented as the graph of a C11 function. The local part in C11 lock is given by the fact that we have two contact angles, and it's expected that the curvature here will explode. So the C11 bound cannot be global, but it has to be local. Okay, but let me turn to the validity of Young's law. And the first interesting result is that whenever we have a minimizer, regardless of the charge, it's always possible to see one of the two inequalities. Again, Young's law was cosine of gamma, the contact angle, equal to beta. We always have the lesser equal inequality. And how do we show it? Okay, so first of all, I will change a bit the picture. You can think that, you can change coordinates in order to have, in order to represent the convex part of your minimizer in this way, using a convex function. The contact set will be here. It's indicated here. And what is the idea? Well, you know that this set is a minimizer of problem, so you can hope to prove a qualitative property of it by using its minimality. And so how do? You do it by building a competitor. So you take a line, which is a hyperplane in R2, and you cut the set. You remove the black part, and you keep only the red part. And you can do this by choosing two parameters. First of all, a parameter r, the distance from the origin, and then an angle parameter theta. And you use the minimality, namely that the functional with the volume penalization evaluated in the set E will be less or equal than the functional evaluated in the competitor. And then you evaluate the difference between the capillarity perimeter term, the non-local energy term, and the volume term. And by sending the two parameters r to 0 and the second parameter theta to gamma, then it's possible to see after some computations that you always have this inequality. Okay, so this is a very good starting result. What could be a possible way to get the second inequality? Well, in this case, we got one by finding competitors from the interior that are contained in the starting set. If we want to prove, well, here the contact angle of the red set, it's always greater or equal, it's always greater than gamma. So we want to do something similar for the other inequality, but from the exterior. But what's the main obstacle to this? Well, we never said that the minimizers are strictly convex, in the sense that we never said that the minimizers arrive in a strictly convex way to their contact points. Indeed, okay, we always have a flat part, which is the contact set, but we could also have other flat parts in dimension 2. And indeed, as you can see here from this picture, it's impossible to build convex competitors from the exterior at any small scale, because it's very clear that you break convexity. So what we want to prove is that, and we are able to do so indeed, if the charge is small enough, then every minimizer of the functional with convexity constraint, it's also strictly convex, in the sense that, okay, there is the contact set, which is flat, but then it contains no segments. And how can we prove it? We can also prove it by building a competitor. Here I represented the set again with a convex function U, and I build this sort of triangle reversed. And as a competitor, of course, I'm assuming the presence of a segment. As a competitor, I consider the new set highlighted in red. Well, it's possible to see that in this case, if the charge is small enough, and if the height of the triangle is also small enough, then this new competitor, the red set, EH bar, has an energy which has strictly less than the energy of your minimizer. But this contradicts minimality. And so for this reason, if the charge is small enough, then you cannot have segments in your interface. This is very good, because in this way, we can prove the second inequality of Young's law, and hence the full equality. So we ask the charge to be small enough so we don't have segments in the interior of the container. And as before, the argument is very similar. Now we are in the position to build competitors from the exterior, again highlighted in red, and we can do it for any small scale. We're going to have an angle parameter theta, which in this case is less than gamma. So with very similar computations, we can extract the other inequality, and hence find the whole validity of Young's law. And this is a pretty good result. So I resumed everything here. If the charge is small enough, not only we have regularity of the interface, but we have also Young's law. Now, before finishing the presentation, I would like to devote some time to a result which we were not able to prove. We spent a lot of time on it, but we only managed to get some partial result. I would like to tell you how it would be possible to get a better regularity for the interface. And this is connected to what I was telling you before, right? So we are using convex sets. So what could be a way to get further regularity? Well, rather than using a competitor argument, we can try and write the Euler-Lagrange equations for the functional, right? But what's the problem? The problem is the set is convex, and we cannot really make local variations without being sure, without breaking convexity, because this is perfectly possible. And what is the condition to make this kind of local variations? Well, okay, the set in the interior, it's strictly convex, its boundary contains no segment. Well, this is still not enough. What we need the so-called strong convexity of the interface. Strong convexity means, on a mathematical level, I mean, at least in this framework, that the mean curvature of the set, which in this case, since it's C11, it's defined almost everywhere, we need it to be always greater or equal than a positive constant. In this way, like having the strict convexity of the interface at the interior of the container, we would be able to actually write the Euler-Lagrange equations for the functional and to use them to prove more regularity. And how would this look like? Well, I need to introduce another tool before showing you the equation. This is still related to the logarithmic measure E of your set E. I told you before that there is always an equilibrium measure. Well, if you take this measure, mu E, and you convolve it with the logarithmic kernel, then you obtain the so-called potential function. And this plays quite a big role in the whole study of the logarithmic energy. The interesting thing is that this is the solution of an elliptic PD Laplacian of the function equal to 0 in the exterior of your domain in R2. And since this is a solution to an elliptic PDE, we can hope to use the function to find regularity. And indeed, it turns out that if you want to write the first variation of this functional in the presence of convexity and in the presence of convexity of the competitors, and so in the presence of strong convexity, the one that I was telling you about before, well, you have that, okay, so the contact set, this is already flat, so it's regular. So you can, and also it's impossible to make variations there. So you only look at the interface in the interior. The first variation of the capillarity perimeter in the interior is the same one that you have for the perimeter, so the mean curvature. And then the first variation of the logarithmic energy is given by the gradient to the power 2 of the potential function multiplied by the charge over 2 pi. And since you have also a volume constraint here, you have that all of this is equal to a real constant lambda. And what's the idea now? Well, the idea now is that if we use the system that the potential function, for which the potential function is a solution to, with some elliptic regularity and a bootstrap argument, basically playing with the Euler-Lagrange equation, you could actually prove that if the charge is small enough, and this would be the result that we would like to prove, then the minimizers are not only C11 lock, but also C infinity lock away from the contact points. And what's the only problem of this? The only problem is what I told you before, is that so far for us, it was not possible to prove this kind of strong convexity of the interface. We managed to get some partial results in this direction, but we couldn't get it in full generality. And so for this reason, we cannot really say up to now that the minimizers are also C infinity lock. So hopefully I was clear in this last part. I was a bit sketchy, but this is the end of my presentation, and these are the main references that I used. And I thank you for your attention.
So thank you, Adriano. Is there any question also from Zoom?
I have one.
Yeah.
Do you have any way of characterizing the Q bar you nominated multiple times? When you say charge small enough, I didn't notice if you characterize it somehow or...
Yeah, so basically the idea of the proof is to, okay, we want to work with a volume constraint in this case, and we need to build a competitor, and you build it by adding some mass, the red competitor. You want to take into account the difference of the mass, but then you want to come back to an actual competitor for the original problem. So you want to rescale it to get a volume 1. The idea is to make a comparison between the energy of the new competitor, E bar H, and the energy of your minimizer E, and you basically write what's the value of the functional. Okay. Since this is given by a rescaled version of the one that you built before, the red one, you can see how the capillarity perimeter and the nonlocal term, what's their behavior under rescaling. And in this way, you have an explicit parameters that determines the rescaling. You can basically prove some kind of quantitative relation between the differences of the perimeter and the differences of the volume. And this is basically given from a Taylor expansion. So to answer your question, there is not a real way to quantify it. We don't have an explicit expression for Q bar, but we know that it exists because it comes from a Taylor expansion. So when you're close enough to 0, you're always gonna have the quantitative inequality between the difference of the perimeter and the difference of the volume.
Okay.
But it depends on the parameters and on the dimension.
Yeah, it depends only on the dimension 2, so it's universal, and the parameter beta from the capillarity perimeter.
Okay.
Okay. Any other?
I have another question, maybe. Can you say something more about this Goldman and Novagher-Ruffini example where they show non-existence of minimizers? Because that is
Okay.
really surprising, I guess.
Yeah, this was quite surprising indeed. And so I don't have a picture for this, but as I told you before, the idea is to build a minimizing sequence for this. So how do you do it? You take a ball with more or less all of the volume, and the remaining part, you divide it in little small balls that you send away very far from the starting one. So then you also need a charge, which is a competitor for the Riesz energy. The idea is to put a zero charge to the big ball and to concentrate all of the charge in the very small balls.
Okay.
So in some sense, this is similar to what I was telling you before, namely that you're concentrating a lot of charge in a very small environment, and the idea is to send these very little balls to plus infinity. So in this way, the perimeter, and also to change, I mean, to make them really small and to send them to plus infinity. So in this way, the perimeter is converging to the perimeter of the big ball, the one with zero charge. And the Riesz energy, since they're going to plus infinity, is converging to zero, because the distance between all of them will be going to plus infinity, and so the interaction will go to zero. And this is possible to, you can always do it whenever the parameter alpha is between 1 and n, and surprisingly for every charge. And it's interesting to say, okay, you can tell me, okay, but this is still a very singular minimizing sequence, right? Because it's not bounded. Well, you can adapt this argument. Let's say that you ask boundedness for your minimizing sequence. So you say, okay, I want to work in a very big compact container. Well, in a very similar way, you can make a similar proof, and in the same way, like you have a very big ball, and then you have a cloud of very small balls with a lot of charge in them. In this way, this is the way you can prove that not only you don't have global minimizers, but also you don't have local minimizers. And not only this, but there's also another result that I didn't mention, and this is from Muratov and Novaga. Well, this is still the last example that I told you. Even if you ask boundedness, you also don't have connectedness. Well, if you also ask a connectedness of the competitors, it's always to take, you take your ball, you modify it in a smooth and L infinity way, arbitrarily close in Hausdorff distance to the ball. Well, also in this case, you can prove that you don't have minimality. You can always make a kind of variation that makes the full energy go below. And so, even if you ask boundedness and connectedness of the competitors, you cannot really get existence of minimizers. And
this even in dimension 2, where connectedness is strong.
yes, even in dimension 2.
Okay.
Even in dimension 2. So this is why you need to modify the functional, and this is why the model is not taking into account of all of the physically relevant contributions.
Thank you.
But do you have a similar result if you replace the perimeter with the P beta instead of?
A non-existent result, you mean?
Yes.
Okay, so we actually didn't prove it, but we expect that if we take the same kind of minimizing sequence, so with very like charge concentrated in very small balls sent at plus infinity, then we should, I mean, I expect that it should be possible to adapt the same argument also in the capillarity case. Instead of working in Rn, you work in the half space. And We didn't do it, but I think it's possible.
You mean instead of B1, you take B beta and...
Yeah, exactly. But also this argument that I described, it's valid not only for B1, but actually for any compact set. Like, let's say that, assume that you have another compact set that could be either a local or a global minimizer. Well, you can adopt the same argument to show that even if you had it, it's still impossible, like it still cannot be a minimizer. So that applies not only for the ball. So I think that it applies also to the truncated balls, minimizing the capillarity parameter.
Okay.
I actually have one curiosity. So if I understand correctly, all of this is without gravity.
Yeah, this is without gravity.
So is there also any literature about gravity, or do you expect?
Yes, there is something, and as far as I know, there are 2 articles, and I mean, fun because it's always a permutation of the same authors. 2 articles by Muratov, Novaga, and Ruffini.
Okay.
So Muratov is, yeah, I mentioned him here for another article. Muratov, Novaga, and Ruffini. They have 2 articles in which they consider, again, same situation, perimeter plus Riesz energy, in dimension 2, so flat droplets. And I think that in one article they study the model, and they also show well-posedness when the parameter alpha is equal to 1. So it's covered also in this result. But then in the second article, they also add a potential energy term, and so you have also gravity. In R3, which is the physical case, not as far as I know, but if you want to look a little bit more into this like big family of non-local isoperimetric problem, there's also another model that I didn't mention today, that is the so-called GAMO, GAMOW, liquid drop model, in which instead of having, instead of taking the infimum over the, instead of changing the measure, I mean, instead of taking the configuration of minimal energy, you just consider the uniform measure over the set. In this way, instead of having the mu and the mu, you have one dx dy, so Lebesgue 2 times, divided by the measure of the set, still multiplied by the same kernel. So in this way, you're like restricting the possible, I mean, you're giving some constraints to the charge. This is still non-local, and there's like a big part of literature devoted to studying this model. And now that one I don't know very well, but it may be possible that someone did it for in this case. I can also tell you that if you take this energy, the gamma energy that I described you right now, there is a work by Giulio Pascale, is in Naples, where he studied a very similar thing to what we did for capillarity. So you have a functional in which you have the capillarity perimeter plus the gamma energy, so not the Riesz energy, plus also a third term, and in that case it could also be the gravity. And yeah, so for sure you have something for the capillarity case. I would say that, I mean, I should look into it, but there may be something also for a perimeter plus gamma plus an additional term.
Okay, thank you. So if there's no other question, I think we can thank the speaker again.
Thank you very much. Thank you very much.
And, see you next Friday.